Welcome. This is a video that explains the calculations for the heat diffusion of ice lab. It might be good for everybody who watches just in case. This is not your data, though. This is fake data. I just made it up off the top of my head. So I should not see this data in the labs. There is another video where I show the whole lab. And if you are a distance student, that is your data. And if it's only one trial, that's fine. Don't worry. Okay, so heat diffusion of ice lab. I printed out a version so that I could have space to really show you the calculations. I highly suggest you doing this on scrap paper and not just on your computer, because I think you're going to want to really show yourself the math. And if you want to do your calculations on scrap paper, take an image of it and submit it with your lab when you actually submit the lab. I would love to see the math you're doing. Okay, here is fake data right off the top of my head. I do want to point out, though, that this number here should be the same for everybody. It should be 100.0 milliliters of warm water because they tell you to measure that, and you measure it with the graduated cylinder. The graduated cylinder has precision to the milliliter, so you get to estimate one place past the precision of the instrument. So the volumes we get here, they should all go to the tenths place. We're working on significant figures. We're working on being more precise with our math. Anytime you have precision, you want to keep it. For instance, this has 4 significant figures now because of the 0.0. This has 3, this has 3, and this has 4. Okay, so my warm water was warm. It didn't decrease all that much, maybe because the ice cube wasn't that big, right? Okay, so I'm going to go through these calculations with this fake data, but I want you to see where the equations come from, where the numbers come from, so that you can do it with your own data. Calculate the volume of water that came from the melted ice. Okay, easy peasy, right? Here is the water and the melted ice after. Here's the water before. This 100 is the same for everybody. So basically it's however much you have over 100, right? So if I were to show this calculation, which is a little bit silly, I have 14 milliliters. Determine the mass of water that came from the melted ice. This is exactly the same, except for the words mass and volume, but the density of water is 1 gram per milliliter. Now, I probably should have put some precision on this. Let's assume that this has infinite sig figs. So guess what? If you have a milliliter, you have a gram. Now, this is only true for water, but it's very convenient. So if I had 14 milliliters of water after the ice melted, that means I had 14 grams of ice. I also want to point out that I'm going to take up a lot of space with these calculations, but you have 4 trials. So you might want to segment this in 4 ways, or just do it on another piece of paper, like I said. Now, see the 14 and the 14? They go here in the calculations table. 14.0 milliliters, 14.0 grams. You will have different numbers, but these 2 numbers should be the same. These 2 should be the same. These 2 should be the same. Okay. Calculate the change in temperature. That is easy, right? Okay, obviously this is going to become a delta T in one of our equations. This is a mass. This is going to be an M, a mass in one of our heat equations. This is also a mass. Okay. Determine the mass of the original warm water, assuming the density of water is 1 gram per milliliter. Now check it out. We should all have 100 milliliters of warm water, so we should all have 100 grams of warm water. That is a number This should be the same for all of us. Okay. This is where our heat equations really come in. Okay. The warm water cooled down. It went through a temperature change. The ice melted. It went through a phase change. So if you look at our heat equations, it makes sense that these are the two equations that are going to be involved. Q equals MCAT is for any temperature change, and Q equals MHF is for freezing or fusion. And all we're doing is we're following the heat, okay, from the warm water into the ice. And the assumption is that the heat, the Q that left the warm water, goes into the ice and melts the ice, that it's the same amount of heat. Now, that is not a perfect assumption. Maybe you can guess where some of your error comes from, okay? But that is to say that here, I'm going to be using Q equals MCAT, and I'm going to be focusing on the heat that left the warm water. And then here, I'm going to be using Q equals MHF, and I'm going to be following that heat into the ice. Okay. I don't know Q. I do know the mass of the warm water. Notice that here I'm focusing on the warm water, so this mass is the 100 grams. When we move to the ice, it's a different mass. Big hint. Okay. What's next? Capital C, specific heat capacity. Okay. C is specific heat capacity. For water, it's 4.18. Water is a great heat sponge. Okay. Just working through my equation, delta T, change in temperature that the warm water experienced, whatever your change in temperature is. There's everything, and I'm multiplying 3 numbers. I'm not going to worry about rounding yet. I'm going to keep more digits than I need because I'm not at my final answer yet. This is my goal, right? Heat of fusion. So this is where I'm going to stop and round. If I did that here, I'm only halfway through my calculations. I'm going to lose some precision. So wait till the very end of your calculations to worry about rounding. Okay. I mean, write something reasonable, but okay. Q equals MHF. This is your heat. The heat that leaves the warm water goes into the ice. So we're going to follow it into the ice. Now I hit the mass, but it's the mass of the ice. So for me, that's 14 grams. And then I hit heat of fusion. Well, here's the thing. I know what it should be, but that's the whole point of this lab. I'm going to pretend that I don't know it. I am calculating this. I'm going to see how good my experiment is. So you could put heat of fusion here, you could put X here, and you're solving for X. So this guy divided by that guy, which makes sense because the units on heat of fusion are joules per gram. Okay? Ooh, that's not bad. I'm getting 483.68 blah, blah, blah. 3 significant figures. 4, 3, 3, 4. It looks like throughout this whole thing, everything is either 3 or 4 significant figures. So I'm going to round to the weakest link, which is 3 sig figs. So this is going to be 484 joules per gram. What do you think? I made these numbers up off the top of my head. Not bad. Not great, but not bad. The real answer is 334. I got 484. The percent error calculation will tell me my error as a percentage of the right answer. Remember that whatever the subtraction is, we really want the absolute value of that subtraction. So this is going to be mine, that's going to be 334, that's going to be 334, and we're going to make sure to subtract before I divide, before I multiply. Okay, so 44. Okay, and again, I'm going to keep 3 sig figs. I am getting 44.9% error, which is not bad considering I made these numbers up off the top of my head. If you did this lab in person, we are going to be competing for the lowest percent error. So if you have trials that are your actual data and you think you have a low percent error, like especially in the single digits or maybe in the teens, basically anything less than 20%, let me know and I will collect all of these things. Now, as you think about the energy, I want you to remember that melting fusion on a heating curve is this line segment. So we should know what is happening with kinetic and potential energy while fusion is happening. I don't want you to be confused by the fact that this temperature is constant, but your temperature kept changing because your thermometer wasn't actually in the ice cube. Your thermometer was in the surrounding water. So these two questions are more about, do you remember how to tell what's happening with potential and kinetic energies there? Okay. For the rest of the questions, it'd be good to check your notes. Okay, that's it, and send me any questions you have.